let's say, if I have, let's say, 0.75, that would be 1 times 2 to the minus 1 plus 1 times 2 to the minus 2. So my binary representation of that fraction is 0.11. Or similarly, let's say 0.625. How would we start that? That's 1 times 2 to the minus 1 plus what's left over is 0.125, which is 1 times 2 to the minus 3. So what's my binary representation? 0.101. So if you like, this is the 2 to the minus 1 place. This is the 2 to the minus 2 place. This is the 2 to the minus 3 place. And so on. In the same way that in decimal, 0.ABCDE, this is the 10 to the minus 1 place, this is the 10 to the minus 2 place, 10 to the minus 3 place, and so on. So it's exactly analogous. Okay. So what we're going to do is we're going to say the notation floor f bar of x sub L of x means the first L of x bits after the decimal place. So we know already for all of these values of f bar can never be greater than 1. So therefore, in fact, f bar can also never be equal to 1 unless you have a letter of probability 0. But we're going to disallow that possibility. So f bar is always less than 1. So that means to the left of the decimal place, all the bits are 0. So in fact, we can ignore all of these. L of x will start by taking the first L of x bits after the decimal place, and that will be how we encode. So, as an example, let's take 0.375. What's the binary representation of that? In the 2 to the minus 1 place, how many 2 to the minus 1s are there in there? 0. So this is less than 0.5, so there's 0 2 to the minus 1s. How many 2 to the minus 2s are there? 1. There's exactly 1. So if I subtract 0.25, I get 0.125. How many 2 to the minus 3s are there? Just 1. And that's it. Okay, so if I took, let's say f for a particular value of x, f bar of x is 0.375, then 0.375 floor 0.375 sub 1 would be 0.0. That's the first bit in the binary representation. If I take 0.375 sub 2, then I get what? 0.01. So I just drop everything else. 0.375 floor sub 3 is 0.11, or excuse me, 0.011, and so on. Because all of the trailing digits are 0, 4, 5, and 6, and so on. You just append zeros to them. Okay, so what's interesting about this the size of the quantization error in other words, f bar of x minus floor f bar of x, so L of x. Well, okay, if I have, let's say f of x has an arbitrary number of bits in its representation, and I take the first L of x, Lx of those, so in other words, I have 0. Let's say for a concrete example, let's say it's this, let's say the binary representation is this, so on and so on, and let's say L of x is 4, so I'm taking the first 4 bits. So the error if I subtract what I get is 0.0000, and then I start here. So everything to the right of there is error. This is the 2 to the minus 5 place, 2 to the minus 6, and so on. So what must be true is that the largest possible value for this error would be as if these were all 1s. So in any case, we can guarantee that the error is less than this if the 2 to the minus 4 place contained a 1. So this error is less than 2 to the minus L of x. Okay, now what I'm going to do is I'm going to select L of x. What we're going to say is that L of x is equal to, now, we said there exists a code, there exist prefix codes with ceiling log 1 over p of x bits. There must exist a prefix code like that. Here I'm going to take ceiling log 1 over p of x plus 1. So I'm taking 1 bit more than I really need to in order to get a prefix code, but it turns out later on that will be good because I can show that using this particular scheme, I can more easily show that this is a prefix code, and in fact that makes this scheme, this particular coding scheme, usable at the cost of just 1 bit. So it's hard to specify a code with exactly ceiling log p of x, but if I'm willing to put up with a 1-bit penalty, then I can use this very simple scheme to get a code. So if I have that, then the magnitude of my error is 2 to the minus Lx, which is equal to 2 to the minus ceiling log 1 over p of x plus 1. Now, if I get rid of the ceiling, then I get a larger value here, but it's 2 to the minus a larger value, which is smaller. So that's less than 2 to the minus log 1 over p of x plus 1. What I can do is I can split up this exponent